Hello guys, Dr. Hasbullah here. So previously we have found the equation for drag in the laminar boundary layer. And in this video we're going to carry on and we're going to find the drag for the turbulent boundary layer. So we know that for turbulent boundary layer, the Reynolds number must be greater than 5 times 10 to the power of 5. So when you have the Reynolds number greater than 5 times 10 to the power of 5, you're going to be in a turbulent region, right? And the velocity profile of the turbulent boundary layer is different from the velocity profile for laminar boundary layer. Okay, let me show you how. Okay, and if we have this flat plate, right? And you have two regions, which is laminar and turbulent. Okay, let's say this is laminar and this is turbulent. And if I take two lines, okay, one is orange in laminar and another one is purple in turbulent boundary layer. And I want to compare the shape of the velocity profile for these two lines. Okay, and if I plot here the graph of y versus u over u infinity, and for laminar boundary layer I'm going to use orange, right? And it looks something like this. Okay, and you know that this can be represented by quadratic or cubic equation, right? But for turbulent, the shape of the velocity profile is a bit different and it's gonna look something like this. Okay, so the change of velocity from the wall is very sharp. Okay, the velocity increases very quickly and it reaches the maximum very quickly as well. And to represent this velocity profile, we can no longer use cubic and quadratic equation. It just wouldn't fit, right? So we're gonna use what we call the power law. Okay, and power law is quite simple. Actually, it's much more simpler than quadratic and cubic equation when we deal with it later. Okay, so for power law, it looks something like this. U over u infinity equal to y over del 1 over 7. And the thing with turbulent boundary layer, the denominator, the 1 over 7, the number 7 can actually change from 7, 8 or 9 depending on where you are in the Reynolds number. Okay, and for y over del to the power of 1 over 7, it is suitable for the Reynolds number that is less than 10 to the power of 7. When you have the Reynolds number between 10 to the power of 7 and 10 to the power of 8, you're going to be using y over del 1 over 8, right? And for Reynolds number greater than 10 to the power of 8, your boundary layer profile is going to be y over del 1 over 9. Okay, so that's how the power law change depending on the Reynolds number. Okay, but for deriving the equation for drag, of course, when you have a different power, which is 1 over 7, 1 over 8, and 1 over 9, you're going to have different equation for drag. At this point in time, we're going to try and use 1 over 7 and derive the equation that gets you the drag equation. I think you are already familiar now with how to derive the drag equation. First, we're going to need the tau, or the wall shear stress. Alright, we know that from the von Karman momentum integral, the wall shear stress is equal to tau naught equal to rho u infinity square d theta over dx, right? And theta is the momentum thickness, right? And theta is equal to y over u infinity square integration from 0 to del, that is u1 minus u dy. And if I bring the u infinity inside, you're gonna have 0 to del u over u infinity 1 minus u over u infinity dy. Alright, and if you remember another equation of tau, okay, is also mu du over dy at y equal to 0. Alright, and previously in laminar boundary condition, we've used this to find the del. Okay, so basically this equation, we're going to equate it with this equation to find the relationship. However, for power law, right, imagine when you have u over u infinity equal to y over del 1 over 7, right? And if you want to find du over dy, you're going to end up with u infinity, and this is going to be 1 over 7 y minus 6 over 7 divided by del 1 over 7, right? And if I rearrange it, this is going to be u infinity 1 over 7 del 1 over 7 times 1 over y to the power of 6 over 7, right? And at y equal to 0, right, if we want to try to satisfy this equation, you're going to have du over dy approaching infinity, right? And this is not right, okay? So basically, this equation cannot be used when we are dealing with turbulent boundary layer. This equation will not give us the accurate wall shear stress close to the wall. So for this, we're going to use the experimental result that is found by someone called Blasius. Alright, and Mr. Blasius has derived an equation that he got from his experiment result, and he tells us that CF is equal to 0.046 nu u infinity del to the power of 1 over 4. Okay, do you remember what is CF, right? So, before that, this is called the Blasius equation. And to solve for the boundary layer in turbulent region, this is very important. What we know from the previous video is CF equal to tau naught divided by half rho u infinity square. Okay, and what do we do with it? We know that CF is now using Blasius equation, so 0.046 nu u infinity del 1 over 4 is now equal to tau naught over half rho u infinity square. Right? So tau naught is equal to 0.023 rho u infinity square nu over u infinity del 1 to the power of 1 over 4. Alright, and this is the tau that we are going to use instead of tau mu du dy, right? And this tau, we're going to equate it with this tau, right? And in order to find this tau, we're going to need to find the theta first. Alright, so I'm going to write this again. So from von Karman momentum integral, we got tau naught equal to rho u infinity square d theta over dx, right? And let's solve for d theta over dx, right? So d theta over dx is equal to d over dx of the theta, right? So theta is actually u over u infinity. This is from 0 to del times 1 minus u over u infinity dy. Okay, and we know that our u over u infinity is y over del to the power of 1 over 7, 1 minus y over del to the power of 1 over 7 dy. Okay, and we're going to need to solve this equation to find the von Karman momentum integral for tau, right? So this is going to be 0 to del y over del to the power of 1 over 7 plus y over del to the power of 2 over 7, right? And we integrate this against dy. Okay, and when we integrate this, you're going to end up with, this is y 8 over 7. 8 and 7, this is del 1 over 7 minus y 9 over 7 del 2 over 7. This is going to be 9 and 7. Okay, and it's time to put in del and 0. Of course, when you put 0, everything goes to 0. And so we need to replace with del. So 7 over 8 del 8 over 7 over del 1 over 7 minus 7 over 9. This is del 9 over 7 over del 2 over 7. Okay, and in the end, you'll end up with 7 over 8 del minus 7 over 9 del. Right? And that means you're going to have 7 over 72 del here. And to put everything back into this equation, so this is d over dx, right? And then you multiply it with rho u infinity square. And this is equal to tau. So now we have solved for tau. And we get here tau using von Karman momentum integral. Okay, and this is our equation number 1. And this is going to be our equation number 2. Alright, so quite simply, tau is equal to rho u infinity square d over dx. This is 7 over 72 del. Is also equal to our equation number 2, that is 0.023 rho u squared times nu u infinity del. So rho u infinity squared times nu over u infinity del, the power of 1 over 4. And remember, this comes from von Karman momentum integral, and this comes from Blasius equation. Alright, and now what we do is we put everything that is related to del on the left, and the rest we send it to the right. Okay, so let's simplify this equation first, right? So I'm going to cancel out rho u infinity square, right? That's quite obvious. Right, and I'm going to bring this del to the left. So this is del to the power of 1 over 4 d del, and move everything to the right. Okay, so this is 0.023 nu over u infinity to the power of 1 over 4. Okay, and this is times 72 divided by 7 dx. Okay, and you're going to end up with 7 times 72. This is 0.237 nu over u infinity 1 over 4 dx. Okay, and this is equal to del to the power of 1 over 4 d del. Okay, and I think it's quite obvious what you're going to do next, which is to integrate both sides. So you will end up with del to the power of 5 over 4 divided by 5 times 4 equal to 0.237 nu times u infinity 1 over 4 x. And if I want del on the left, what I'm going to do is I'm going to leave del here, 5 over 4, and this becomes 0.237 times 5 over 4. This is 0.296 nu u infinity power of 1 over 4 x, right? And if I square root everything with 5 over 4, so I'm going to square root everything with also 5 over 4, so I'm going to end up with del equal to 0.296 296 to the power of 4 over 5 times nu over u infinity to the power of 1 over 4 to the power of 4 over 5 x to the power of 4 over 5. And I'm going to end up with 0.296 to the power of 4 over 5. And this is going to be 0.378 nu over u infinity 1 over 5 times x to the power of 4 over 5. Now I can do a little bit of manipulation so that I have the Reynolds number term on the right hand side. So I'm going to multiply this with x 1 over 5 over x 1 over 5. Right, so what I'll do here is basically I want this x to go into here. So this will form the Reynolds number. Right, and x to the power of 4 over 5 times x to the power of 1 over 5 is just x. Alright, so you'll end up with the final equation for del is 0.378 x, okay, and this is divided by rex to the power of 1 over 5. Okay, there you go guys. This is the relationship between del and x. Okay guys, so try and practice to get this relationship between del and x. Okay, try it over and over again until you can do it without looking at this video. And then you can continue and carry on and finish the derivation of the drag force. Okay, so good luck and I'll see you soon. Bye.